The data of any process which is under control are normal distributed if the data were measured on a cardinal scale. The data for lead times might be skewed, but in a controlled process you will only find random variation of data within a normal distribution. Control charts serve to check whether there are suspicious extreme values or patterns in the data. A control chart can detect the signals in the data that point to systematic variation in the process. During the first week after implementation of improvement measures, there were a lot of signals in the data, indicating that in the first week the process was not yet under control. To demonstrate this, I choose the IMR control chart. The upper chart with the individual values shows the chronological sequence of the ratings on the x-axis and the rating values on the y-axis. The lower moving range chart also shows the chronological sequence for this data, but for the differences from value to value. Thus, the first value in the moving range chart is the second in the sequence. It shows the absolute difference between the second and the first value of the individual chart above. As you can see, these data vary systematically, and they obviously do not follow the normal distribution. Overall, 6 statistical tests for the recognition of systematic patterns were positive. In the individual chart, test 1 indicates an extreme low value. Test 2 indicates a suspicious number of values in a row on the same side of the center line. Test 3 indicates a trend with several points in a row all increasing or decreasing. And test 4 indicates that there are several points in a row alternating up and down like a ping pong. For the moving range chart, the test 1 also indicates an extreme value, and test 2 points on several values in a row on the same side of the center line. To get the process under control, each systematic event should be analyzed for its root causes, and they should again be eliminated with appropriate solutions. This strategy might become a little cumbersome, but the result can be a controlled process with only random variation. After we brought the process under control, I calculated the process capability to compare the before-after improvement. Number 1 shows that the target as well as the specification limits are the same for this comparison. You can see that we achieved a significant increase in the rating of taste of the chocolate cookies from grade 2.46 to 1.65, and the target value is 1.5. Related to the customer requirements, we have improved the taste of the chocolate cookies for about 3 sigma levels, from setbench 1.93 to a sigma level of 4.9. The focus is now on the statistical significance and practical relevance of the improvement. Now we check the degree of improvement our measures achieved and test the hypothesis there is a difference in taste between the states before versus after process improvement. If you now read these results, you will recognize that this t-test led to a significant result. The new cookies taste 0.81 grades better than the old ones, and we are convinced this has a practical relevance for our customer and thus for our bakery. The focus is now on the degree how good the target for the chocolate cookies was achieved. Did we achieve our target of 1.5 grades for the rating? Here we test the hypothesis. There is no difference in taste between the rating and the target value. To do so, we used the one-sample t-test to test our sample against this value. And the result is again significant. What does this mean here? Number 2 shows a mean value for the taste of our new cookies of 1.65 with a confidence interval from 1.57 to 1.73. We hope that the target value 1.5 would be included in the confidence interval, so that the difference would be close to 0. But this is not the case. There is a difference between the taste and the target, and this difference is significant. Although we improved the taste of our cookies, we did not reach our target. Please note that in this type of target achievement testing, we want to keep the zero hypothesis. And you remember that this intention is similar to the normality test, where we want the difference between the distribution of the sample and the normal distribution to also be 0. The positive aspect of this result is there is still potential for improvement. And we know our problem. The knowledge of problems in a company is a prerequisite for improvements. If you do not know your problems, you might spend resources for undirected activities. Thus, our plan is to now focus on the sustainability of the improved performance and on its continuous improvement. This is the end of our Six Sigma course. Thank you for your participation and for your patience. Let me please say it in Six Sigma language. Thank you for entering the learning process as an input. I hope that my activities carried out by my resources and guided by my methods could transform you into such an output that you are satisfied because the knowledge, the competence and the motivation you acquired are within your tolerance corridor concerning quality, the processing time and the resources you spent. If you think that your yield is below your specification limit, or if I even missed a must-be, then please let me know. And feel free to also give a feedback if you reached your targets or if you even detected a delighter in this course. For me it was a big challenge and experience to design and implement these modules. Thanks to Holly Ott and Martin Grunow, who granted me all the degrees of freedom I needed. Auf Wiedersehen.